Fundamental Theorem of Calculus, Part 2, Integral Evaluation Theorem. If f is continuous at every point on the closed interval from a to b, and if capital F is any antiderivative of f on a to b, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. So this is telling us how we can evaluate a definite integral with a lower and upper bound. It's telling us that the value of the integral for f of x from a to b is equal to the antiderivative at the upper bound minus the antiderivative at the lower bound. The value that results from this can be interpreted as the net change of the antiderivative f of x from a to b. So we want to understand that when we evaluate an integral of a function, we are calculating the net change of the antiderivative of that function along that interval. And this will allow us to now have an algebraic way to determine the area, or the net area, I should say, between the function curve and the x-axis, as opposed to our previous method of drawing the function that we had and identifying what shape resulted along that interval, and then identifying the appropriate area formula that was necessary to calculate that. And when we had shapes that we couldn't identify an area formula for, we had to use approximation methods, right? Our LRAM, RRAM, MRAM, trapezoid methods, to get an idea of what the area would be. But now, introducing the second part of the fundamental theorem, this is how we are going to calculate the value of our integrals. Antiderivative at the upper bound minus antiderivative at the lower bound. So let's look at some examples on how this is applied. All right, first example. We have to integrate from 0 to 1 of x squared plus square root of x dx. We know that this is going to be determined by calculating the antiderivative of the function within, evaluated at the upper and lower bounds. So we have to determine what the antiderivative of that function inside of the integral would be. So we are looking for a function that when we take the derivative of that, we get what's inside of there. Now, if you want, this is kind of a long approach, but when I see two functions being added together, I can split the integral. And then evaluate each one individually if we want. Okay? So, what is the antiderivative of x squared? Well, when we take the derivative of a power function, we know, so let's say f of x is equal to x to the n. So we have some power function. We know that its derivative is going to be multiply the function by the exponent and then subtract 1. So to reverse that, imagine if that already occurred. To reverse it and get back to where we started, we have to add 1 to the exponent and then divide by that new exponent to cancel out that order. So again, what this is saying, to get from the function to the derivative, we multiply by the exponent and then subtract 1 from exponent. So that's how we get the derivative. But what if we want the antiderivative, capital F? We have to reverse that process. So the first thing we're going to have to do is take this order that goes from multiplying to subtracting. We're going to have to reverse that so that we have to first add 1 to the exponent and then divide by the new exponent, by that new exponent value after we've added 1. So let's see if that works. So we're going to reverse that differentiation rule for power functions. So if I add 1 to the exponent, I get 3, and then I have to divide by that new function, and I get 1/3, or x cubed over 3. So x cubed over 3, which is equivalent to 1/3 x cubed. Now, to check to see if my antiderivative is correct, if I take the derivative of this, I should get what's inside of my integral. And when I apply that power rule for differentiation, I get x squared. So 1/3 x cubed is the antiderivative. And we have to evaluate from 0 to 1. So I'm going to start using this notation, which is going to tell us that this is equal to 1/3 1 cubed minus 1/3 0 cubed, which is equal to, well, anything times 0 is 0, 1/3. Now we have to do the second part, which is here. So I'm going to move this over. Just like with differentiation, when we deal with radical functions, so we're looking for a function whose derivative is the square root of x. Let's rewrite it as a power function. We like power functions. They have nice rules. So applying the same idea as I did before, we're going to add 1. So we're going to get x to the 3/2. And we have to divide by that new exponent, so dividing by 3/2. Now, dividing by a fraction is the same thing as multiplying by its reciprocal, so it's multiplying by 2/3. So this is what I think is the antiderivative of x to the 1/2. To check, if we take the derivative of this new function, do I get x to the 1/2? And the answer is yes. So this is the correct antiderivative, and we're going to evaluate this from 0 to 1, which is equal to 2/3 1 to the 3/2 minus 2/3 0 to the 3/2, according to the fundamental theorem, part 2. Antiderivative evaluated at the upper minus antiderivative evaluated at the lower. Times 0 cancels, and we're just left with 2/3. So I broke this original integral into two pieces, so to get the final result, we add these two things together. 1/3 and 2/3 is equal to 3/3, so the value of this integral, or the evaluation from 0 to 1 for that function, is just 1. And geometrically, the interpretation for that is it is saying the area, or the net area from 0 to 1 for that function is 1. And before we move on to the other examples, let's establish the power rule for integrals, or integration. So if we have a function, f of x, and we're looking for capital F of x, or f prime of x, and our function is defined as a power function x to the n. To get the derivative, we know we multiply the function by the exponent and then subtract 1. To get the antiderivative, we have to reverse that process, so we know that we have to add 1 and divide by the new exponent. So here are your power rules for the derivative that we already know, we've already worked with, but now a power rule for finding an antiderivative. So because it's that simple, we want to take advantage of applying this power rule as often as possible. Now, there's one exception to this rule. So let's make a note of the exception that we want to be on the lookout for. Is when we have the function 1 over x. Okay? So when we have the function 1 over x, you may be inclined to rewrite it as a power function, which is the same thing as x to the negative 1. But when you apply this antiderivative rule to the power function, when we add 1, we get x to the 0 and dividing by 0. Well, we can't divide by 0. So there's the exception to this rule where applying it will not reveal the antiderivative of that. So what we have to do is think, is there a function we are familiar with whose derivative is 1 over x? And the answer is natural log of x. Okay, so that's the one you want to pay attention to if we were to take the derivative. If we redefine it as this, taking the derivative of this, we can apply the power rule to, but taking the antiderivative of this, we cannot. So this is the one function we want to be careful with. So we can move that to the front, subtract 1. So here's our derivative and our antiderivative, okay? So we cannot apply power rule to this function to find an antiderivative. So we have to think what function's derivative is 1 over x. That's ln x. So I just wanted to bring that up. So when we jump to this next example, we can apply that. So we know to evaluate the integral, the definite integral, we have lower and upper bounds. We're going to find antiderivative, evaluate it at the upper bound and the lower bound, and find the difference. So what's the antiderivative of 2 minus 1 over x? Well, the antiderivative of 2 is 2x. The antiderivative of 1 over x we just brought up is ln x. So again, you may, if you forget that, you may be inclined to try to reformat that as a power function, but what you should recognize, and what should stop you in your tracks, is getting this, okay? X to the 0 over 0, can't divide by 0. So rethink that. Now, we're trying to evaluate this from 3 to 1/2, so this is going to equal the function evaluated at the upper bound minus the function evaluated at the lower bound. So we're going to have 6 minus ln 3 minus 1 minus, or sorry, plus ln of 1/2. So we can say 5 minus ln of 3 plus ln of 1/2. And we can take this one step further. If we say we're going to do minus, we're going to pull out a negative here. So we have ln 3 minus ln 1/2. So when we subtract two logarithms of the same base, we can combine it into one by dividing what we're taking the log of. So we can say minus, and it's going to be ln of 3 divided by 1/2. Dividing by 1/2 is the same thing as multiplying by 2. So this is 5 minus ln 6. So this would be our final answer for the value of that integral from 1/2 to 3. So a log property there where we can combine those two things together into one to get a fully simplified result. Next example, let's say we have to integrate an exponential function of base 3. Now you'll notice on this one that the lower to upper is not going from least to greatest. The good news is that this theorem, the fundamental theorem, will take that into account. Its sign, we don't have to do anything to it. If we want to flip it, just make sure you make it negative, that's fine. But the act of finding the net change in the antiderivative from the lower to upper, because it's a net change, the sign will take care of itself. All right, so what's the antiderivative of 3 to the x? Well, to figure that out, let's take a look at what the derivative of an exponential of any base a, or any base is. We know it is itself, so let me put some notation to this. We differentiate, it's going to be itself times ln of the base. So if we have 3 to the x, if we were taking the derivative of that, we know we would get 3 to the x times ln of 3. So if I look at 3 to the x as if a derivative has already been taken, so 3 to the x is the result of differentiating a function, then we'll notice that this thing's missing here, this ln 3. So if we just divide instead of multiply by the natural log of the base, let's see if that works for our antiderivative of an exponential. So here is what we think the antiderivative is. Let's take the derivative of it. Remember, ln 3 is just a constant, so we can essentially think of that as multiplying 3 to the x by some number. So differentiating with a constant, we just pull the constant out. And then the derivative of 3 to the x is 3 to the x ln 3, so these cancel, and we get 3 to the x, which is what we want. So the antiderivative of an exponential function is that exponential function divided by the ln of the base, where the derivative of it would be the exponential function itself times the ln of the base. So the antiderivative rule we'll derive before we finish this problem up is if we have a function a to the x, we know its derivative is, actually, we'll stay consistent with what we did in the previous power rule example, if our function is a to the x, we know its derivative is itself times natural log of the base, where its antiderivative is itself divided by the natural log of the base. So there is your rule for antiderivatives of exponentials. Now, if we have e to the x, then applying this, we'll have e to the x over ln e, but ln e is just 1. So the antiderivative of e to the x is e to the x, and the derivative of e to the x is e to the x. So those are the easy ones. But if we don't have base e, know that the derivative is you multiply by the natural log of the base, whereas the antiderivative you divide. So we have discovered what the antiderivative should be. So let's finish out this evaluation. We have our antiderivative equaling 3 to the x over ln 3. And we want to go from 2 to negative 1. So we're going to have 3 to the negative 1 over ln 3 minus 3 squared over ln 3. So the antiderivative at the upper bound minus the lower bound. We're going to clean this up. So 3 to the negative 1 is 1/3. So that's the same thing as 1 over 3 to the ln 3 minus 9 over ln 3. If we want to combine these, we need common denominators. So I'd have to multiply the second ratio on the top and bottom by 3. So we're going to have 3 ln 3 minus 27 3 ln 3. We can combine into negative 26 3 ln 3. And there is the value of the integral from 2 to negative 1 of 3 to the x dx. Now, if we flipped that integral, okay, so we went from negative 1 to 2, we would just have to pull a negative out in front, and you should get the same exact answer. So the fundamental theorem takes care of the fact that we may be working from greatest to least or least to greatest. That net change in the antiderivative will take the sign into account for you, which is nice. Next example, let's look at a trig example. When I see a constant multiple based on our integral properties, we can pull out that 2 if we would like. So that's an optional move. Then to evaluate the integral, we're going to have to do 2 times the antiderivative of sine. So what function whose derivative will give us sine? So make sure you're not taking the derivative inside. We're doing antiderivative. So cosine gives us negative sine. So negative cosine must give us positive sine. So it's negative cosine. And we're evaluating at the upper and lower. So this is going to equal 2 times negative cosine of pi minus negative cosine of 0. 2. Cosine of pi is negative 1 times negative 1 is positive 1. Cosine of 0 is 1, negative 1, so plus 1. So we're going to get 2 times 2, which is 4. So the value of the integral from 0 to pi of 2 sine theta d theta is 4. And then let's look at an example like this. So here we have a composition. We have not discussed the technique we will apply to a function that has a composition in the integral. So at this point, what we can do is we can expand that binomial and rewrite the integral. So r squared plus 2r plus 1 dr. This is the same exact integral, just formatted in a different way. And the reason we're doing that is to break it down into multiple power functions and a constant function, as opposed to having a composition of a quadratic. So now applying our power rule to find antiderivatives, we add 1 to the exponent and divide by that new exponent value, or you can think of multiplying by the reciprocal of that new exponent value if you prefer that. Plus, add 1, so it becomes a 2, divide by 2, so we're just going to get r squared, and then plus r. So this is our antiderivative, and we're evaluating at the upper and lower bounds. Now, just to make sure that this antiderivative is correct, if we take the derivative of that, we should get what we have inside here. So taking the derivative 1/3 r cubed is 3 over 3 r squared, so that's good. And then 2r and then 1. So this checks out, so let's evaluate. So here we have 1/3 becomes 1 cubed plus 1 squared plus 1 minus, at the lower bound, 1/3 negative 1 cubed plus negative 1 squared minus 1. So let's clean this up. We're going to have 1, so 2 and 1/3. So that's going to be 8/3. And then over here, we're going to have negative 1/3 plus 2 minus 1. So there we're going to have 1 and 2/3, which is 5/3 minus 3/3, which is 2/3. So minus 2/3, which equals 6/3, which is equal to 2. Oops, sorry. We have a mistake here. Negative 1 squared is not 2, but rather 1. So we're going to have 2/3 minus 3/3. All right, a lot of mistakes here. Let's back this up, because I screwed up the first one as well. So we're going to have 1/3 plus 1 plus 1, which is 2 and 1/3, which is 7/3, not 8/3. Then here we're going to have negative 1/3 plus 1 minus 1, which is going to be negative 1/3. So we're going to have minus a negative 1/3, which is going to be a plus 1/3, which is 8/3. So screwed up some fraction, went a little too quick, but I apologize. So there's the correct answer. But the point of this problem was to illustrate for the composition, we can expand that out to reveal multiple power rules, constant rules for our antiderivatives. And at a later video, we will discuss how to handle composition if you want to avoid that in the future. So I think that is all of the examples I have, and that concludes the video for part 2 of the fundamental theorem.